Hi, this is Dr. Justin Esarey, and this week we're going to talk about assessing discrete or limited dependent variable models. There are many ways that we can assess how well a discrete or limited dependent variable model fits its data set, both inside of a sample that was used to create the model or fit the model's parameters, and outside that data set in terms of how well it can predict data that wasn't used to fit the model's parameters. And I'm going to talk about a few different approaches to assessing these models first, and then show you some examples of how these approaches are instantiated. From where I sit, the biggest distinction in distinguishing between model fit on a discrete dependent variable model is whether we assess a model's classification ability or its ability to predict probabilities. Let me give you an example of what I mean here. So a classification problem is one where we're trying to sort data into one of two categories. If we have a dichotomous dependent variable, y can equal 0 or y can equal 1. And the model is trying to take some information that we observe about a case on some dependent variables, and then say, well, based on the dependent variables I observe, I'm going to predict that the dependent variable is either a 0 or a 1. So this is going to be a success or failure, a war or peace, vote or not vote, Republican or Democrat, who knows, some kind of binary or in some cases multinomial dependent variable. And in order for, and when we assess a model's classification ability, we ask how many times did it put observations that turned out to be zeros into the 0 bin, and how many times did it put observations that were 1s into the 1 bin. So the question here is, how well do we separate y equals 0 from y equal 1 on the basis of observable variables, independent variables? It makes a lot of sense in certain contexts. Probability basis is a little bit different. In this case, we're going to say that there's some probability that y equals 1, which is in the dichotomous dependent variable case going to be 1 minus the probability that y equals 0. All right? And we're going to be able to we're going to try, rather, to use a model to look at some independent variables and try to guess what this probability should be on the basis of what we see. So, for example, if I'm trying to predict how often a coin will come up heads, right? A two-sided coin will come up heads. I might be able to measure all sorts of characteristics about that coin, its balance, its size, what features are on the coin, what it's made of, all kinds of stuff, and be able to come to some judgment about what probability that coin will come up heads when I flip it. But I would never expect to be able to sort coins into categories where, well, this coin always comes up heads and that coin always comes up tails. It doesn't make sense because the underlying data generating process we know is going to be probabilistic. And so the point of the model is to correctly predict probabilities. So the question that you ask when you assess the model's probability characteristics is how close is the model's predicted probability that y equals 1. We'll just abbreviate this up here, pi, to the observable or observed pi. Now, the trick with probabilities is when we have data sets, we often don't necessarily see a pi. what we see is an outcome, a 0 or a 1. But that doesn't mean that if we ran the model many times over and over again, we wouldn't be able to, I'm sorry, I shouldn't say the model. If we were to repeat an observation many times over again, we wouldn't be able to derive a probability out of that observation. So imagine, if we're talking about international conflict, imagine taking a particular dyad to countries at a particular year and repeating that dyad in time over and over again and seeing how many times that dyad broke out into a war in that year and how many times it didn't, on the basis of random events that may or may not be happening in those countries and in the world at large. If you want a simpler example, just imagine that coin. We flip it once, we get a head or a tail. We flip it 1,000 times, we get a probability density. We get a probability distribution. We get a binomial probability distribution. We can estimate pi. We get a bunch of ones and a bunch of zeros, and we can estimate what the probability of that coin coming up heads really is. And so, as you've already probably guessed from the discussion, which of these approaches makes sense depends on the data generating process. Some data generating processes really lend themselves well to the classification approach. In particular, they lend themselves well when the underlying data generating process really is truly binary and not probabilistic. So let's give some examples of DGPs where this makes a lot of sense. We can start with applied examples from well outside the social sciences. Something actually that goes back to one of the origins of discrete dependent variable analysis, radar detection. So in radar detection problems, there's a big dish that sends out a radar signal, and it reflects off of stuff that might be flying around in the air and buildings in the ocean and all kinds of stuff, and then you get a return signal. And the question is there an airplane in some sector of the sky? And we're going to say yes or no, depending on the signal that we observe from our radar dish. Now, the truth is that there really is a plane there or there really isn't. There's no probabilistic. The plane does not appear and disappear at random as it flies through the sky. It's there or it's not. And so what we're trying to do is we're trying to say, okay, there's some kind of radar signal that we see, reflectance or something, and we're going to pass that through a link function, and if that link function is bigger than some critical value, then we're going to say there's a plane there, and if not, then not, right? We're just going to say there's not a plane there. That makes sense because there really is a plane there or not. And in principle, if our instruments were good enough, we might well be able to develop a model that perfectly classified. We could. It would not be ridiculous to expect that we could perfectly classify cases where there is a plane in a sector and where there's not, because in truth there really is or there isn't. On the other hand, there are clearly cases that are not classifiable. For example, coin biasness. If we're trying to model coin outcomes, right? So I'm trying to assess how biased a coin is. It doesn't make sense to assess the quality of that model on the basis of whether it can predict heads and tails with unfailing accuracy, because the underlying data generating process is not set up that way. No model would be able to always tell me when a coin will come up heads and when it will come up tails, because that outcome is partially irreducibly random. The best I can do is to come up with a probability that the coin will come up heads or tails, and to accurately report that probability to you. So in other words, I'm giving you the information at the limit of randomness. That's the most I can know, given that there's some irreducible source of randomness in the model. Those are sort of clear-cut physical cases. Of course, all the interesting cases are in the questionable area in between. For example, things like war or civil conflict. Is that deterministic, or is that partially irreducibly random? Well, that I think is at least in part a theoretical question. There are some reasons to believe that there is at least a portion of the variation in conflict occurrence that is irreducibly random. That is to say, if we knew everything there was to know that was systematic about conflict processes, we would still at best be able to tell you a conflict will probably or probably not break out between some dyad or some groups in society or whatever. What about voting? You can think about both the turnout decision and the choice decision. Could we, if we knew enough about a person, know for sure whether they would turn out to vote and who they would vote for? Or are those choices at least in part determined by random and ultimately unobservable factors like transient psychological moods and pressures placed on the individual from this, their transient pressures, I should say, not systematic pressures that come up at work or among their peer group or whatever, international and national events of importance that are effectively unknowable a priori. If voting choices are partially irreducibly random, then it makes sense to assess them as random. If they're in principle classifiable, it makes sense to assess them according to classification statistics. So the first thing to say is these are really two different ways of thinking about how well a model fits data. And one thing I hope that you take away from this discussion is that, first of all, they are different. Secondly, they're different in theoretical ways. And then this is sort of the punchline of this. These assessments can give different answers. And I'm actually going to say they can give misleading answers about the quality of a model's fit. When they are applied to an inappropriate DGP. And to go back to our previous example, if we tried to classify coin flip outcomes using a coin probability model, it would always say that we're doing badly. Unless the coin always came up heads or always came up tails, there would always be an irreducible source of error, and our classification assessment mechanism would always say, well, you're misclassifying some cases, naturally. The radar detection algorithm, if you try to assess this with probabilities, it may tell you that, for example, when I say there's a 20% chance of being a plane there really is a 20% chance of being a plane there. But it can also hold you back, because in principle I can develop models that completely cut the cases into 100% and 0% chances. And just because my model gives accurate probability feedback doesn't mean it's a good model. I mean, I want my radar algorithms not to tell me that there's an 80% chance that a plane could be there. I want them to tell me that there is a plane there or that there isn't. So it's important to think about whether these assessments are applicable to the DGP in question before applying them. So now what I want to talk about is some examples of these different types of assessment mechanisms. First, I'm going to talk about a few different assessment mechanisms in the classification type family. Percent correctly predicted, the expected percent correctly predicted, and the ROC curve. And then I'm going to talk about some probabilistic assessment mechanisms. In particular, the Hosmer-Lemeshow curve, which is just an application, the Hosmer-Lemeshow statistic, which is just an application of a binning type algorithm, and then a non-parametric extension of Hosmer-Lemeshow that Andrew Pierce and I recently developed. So the percent correctly predicted and expected percent correctly predicted are classification-based fit assessments. And what they do is categorize an observation as predicted to be a 1 or a 0. If this is a dichotomous, we're going to assume a dichotomous dependent variable, according to the predicted probability of the prediction model. So, for example, I might have a model that says that the probability that y equals 1 is, some function of x beta where, f is the logit or something. This is a GLM model. Or it might be something more complicated like a cart model or a regression tree or something where the fitted probability has to do with the number of cases in the bin that equal 1 or something. But somehow we get this probability. And what the PCP does is say, if this probability is greater than some threshold, t, then we predict y is a 1, a success, a yes, conflict, whatever we're trying to predict. And if this probability is less than or equal to the threshold, then we classify it as a 0. And then we simply say, what proportion of these predictions did we get right? We can do them combined, or we can do them separately. So if we're going to do them separately, we say just what's the number of observations for which y equals 1, given that we said it was going to be 1, divided by the total number of observations for which we said there was going to be a 1. So this is the, percent correctly predicted for 1 cases. For 0 cases, we look at the number of cases for which y equals 0, given that we said it was going to be 0, over the total number of cases that we said were going to be 0. And if we want to combine these, we just look at the number of correct matches over the total number of observations in the data set. So that's the unified percent correctly predicted statistic. And quite often this is what you'll see reported in papers. Although in my mind, very often these breakout statistics are actually more important because it's often harder to predict one category than another in an applied case. So consider, for example, how easy it is to predict that there won't be a war tomorrow in some dyad. Yeah, if I just say no to all of them, there won't be a war in every conceivable dyad, I'll be right almost every time. It's much harder to pick the correct cases where I say there will be a war and there actually will be one. That's much harder. So it's, I think, useful to see these statistics broken out by type of prediction. And some software packages, and papers will do that. But sometimes they'll just report a unified statistic like this. That's all there is to it. That's a pretty simple, straightforward way of thinking about a problem, is the percent correctly predicted. The expected percent correctly predicted, which was proposed by Mike Heron in the 1999 volume of Political Analysis. I'm pretty sure it's Political Analysis. Pretty sure it's 1999. I could be wrong about both of those, but I think it's 1999 Political Analysis. Is just a modification of this idea that accounts for the fact that PCP forces us to set a threshold, t, and the choice of t is quasi-arbitrary. Like, we often pick 0.5 as the cutoff, sort of which one has the greater probability of occurring. Doesn't necessarily have to be 0.5 though, could be something else. Some papers do use other values. And the EPCP sort of tries to recognize that choice of threshold is arbitrary. And so what it does instead is it tries to calculate the percentage of the time that we would have made the correct prediction by saying that if, for example, probability of y equals 1 is, say, 30%, and we actually observe it as a 1, we would have gotten it right 30% of the time. That's the way I understand the logic. The actual computation is pretty simple. You just sum up all the cases for which y equals 1 and sum their probabilities, where pi is probability y equals 1 for observation I. And then, to that, you add the sum for all the y equals 0 cases of 1 minus pi hat. 1 minus pi hat I. So in essence, you add up the probabilities for all the times you would have correctly predicted a 1, and the probabilities for all the times you would have correctly predicted a 0, and divide by n to get the expectation, and that's your expected percent correctly predicted. It gets rid of the threshold arbitrariness by you no longer have to choose a t. In some sense, you're sort of choosing pi as t. That's a little bit misleading. What you're doing is you're saying that if whatever your pi prediction is, that's the percentage of the time you would have gotten it right. So if I say, there's a 40% chance of war breaking out, it's sort of, you can think about it as saying 40% of the time I say 1, 60% of the time I say 0. So you get credit for a correct prediction 40% of the time. That's sort of how it works. It's still a classification-based statistic, though, because it's ultimately still about saying how many times did we file an observation correctly according to the y we observed. So it's still firmly in the camp of classification-based statistics. In the case where the DGP really is classifiable in this way, you get good separation in the data generating process, it's conceivable to have a PCP or an EPCP of 1. And effectively what you're trying to do in these cases, if you can imagine, let me start with this. So if you can imagine an axis where this is y, of course it takes on two values, 1 and 0, and this is x, what you're trying to do is come up with a set of variables such that you can perfectly separate them, and the fitted, if you're fitting a logit, for example, the fitted logit will try to, not the best drawing in the world, do something like that. In fact, R will report an error in these cases. It will say, oh, you got perfect separation, which you can sort of think of as bad, because when you try to estimate the logit for your coordinate here, for your variable here, x, the beta is actually undefined. The beta hat will tend to run away to infinity to make that sigma get as tightly S-shaped as it possibly can. So technically beta is unidentified or infinity, depending on how you want to think about it. But actually that's really good if this is a classification problem, because what that means is x separates the variables perfectly. It's a really good classifier. And so in problems like this, what you're trying to do is you're trying to add dimensionality to the prediction problem until you can separate the cases really cleanly. And of course, you don't want to add junk dimensionality. That's why we do out-of-sample assessment, which we're going to talk about in the R section of today's lecture. In other words, we don't want to just keep adding dimensions until we get one observation in every dimension. That would be stupid, and it wouldn't give us a very good separation out of sample, prediction out of sample. But that is what we're trying to do, is get perfect separation out of sample. And if we can do that, we should get a PCP that looks, it's 1, 100% perfectly correct prediction. So I'm going to use my earlier R script for CART and random forest models to show you how you can do these fit assessments in R. And I'm going to start with the percent correctly predicted statistic. So I'm loading in the Titanic data set that we used in that earlier lecture. And the Titanic data set is a list of passengers on the Titanic, not a complete list, I believe, but a list of people on the Titanic and whether they survived or died, and some various characteristics about them, like which passenger class they were in, how old they were, whether they were male and female, and so on. The first thing I'm going to do is split the data into prediction and training data sets to avoid the problem of overfitting. I don't want to give a model credit for simply coloring lines between every single point. I want it to fit the data closely, but I want it to be able to repeat that fit on a set of data that it hasn't seen. In other words, a set of data that it can't use in order to fit its parameters. So the training data is what I'm actually going to use to fit my models, and the prediction data is what I'm going to use to test the models. And I've split the data roughly in half for this purpose. And this order statistic just creates a random ordering so that I'm picking passengers at random for inclusion into the training and prediction data sets. I'm going to start with a really basic GLM model that predicts survival on the basis of which class of ticket a passenger held, first class, second class, or third class, whether they were male or not, their age in years, whether they had any siblings on board, and I actually think that, let's see, it would be Titanic $3 $. Yeah, this is actually the number of siblings they had on board, because this maxes out at 8. And that's it. That's all that goes into the model. Oh, and one more thing, an interaction between the class of ticket and gender, on the theory that females may have gotten off even if they were in second or third class, but males were more likely to die in second or third class. So we allowed the model to take on that flexibility. In order to compute the percent correctly predicted, all we need to do is just use the predict command in R to generate predictions out of our GLM model. We want responses, which are probabilities, and I do in-sample predictions on the training data that I use to fit the model, and I use the prediction data set to do out-of-sample predictions on data that I didn't use to fit the model. So the percent correctly predicted fit statistic is pretty simple. All I have to do is just pick a threshold, a cutoff, and decide which of the predictions are less than or greater than the threshold I've picked. So in this case, I've said that survivors are people who have, I'm predicting survival for anyone who has a probability of survival of greater than a half. Then I look at my training data set, and I simply say, okay, which people did I predict to survive? How many of those people actually survived? So I sum up the survival variable for the people I think survived, and I divide by the total number of people that I said should have survived. In this case, we get an answer of about 81% in sample. So I'm correctly predicting 81% of the survivors in my sample. To predict fatalities, I just create a variable called die-logit, which says which people am I predicting to die. So these people have fitted probability in sample of less than a half, less than 50% chance of surviving, 50% chance of surviving. And then I look at the sum of the people I predicted to die, how many of them survived, as a proportion of the total number of people I said would die. 1 minus that will give me the proportion of people who died as a proportion of the number of people I said would die. And that proportion is about 80% in sample. Now, those are my in-sample numbers. For the out-of-sample PCPs, I just repeat the process, but instead of specifying the in-sample predictions and the in-sample data set, I use the out-of-sample predictions. So you can see I'm using OOS predict here. And I use the out-of-sample data set, Titanic.pred. And so in terms of survivors and fatalities, I predict 74% of the survivors correctly and 78% of the fatalities correctly. So a bit worse than the in-sample case, as we would expect, because my model hasn't had a chance to adapt itself to this data. But still pretty good. 70, the numbers don't change all that much when we go from in-sample to out-of-sample. So that's, generally speaking, that's pretty good. We are doing a good, I would say that this model is doing a fairly decent job of classifying passengers on the Titanic correctly as either survivors or fatalities. So the expected PCP is just as easy to compute as the PCP. In this case, what we want to do first is in-sample and out-of-sample. Identify the people who survived in the training data set and in the prediction data set for in-sample and out-of-sample respectively. So we'll start with the in-sample training data set. So now I've got who survived and who died. So for example, if I type in survivors here, you'll see there's a list of everyone who survived by index number. Then what I do is I say, okay, I need to take out all the NAs because there are some NA predictions if there's missing data in this data set. Look at all the people who survived. What did I predict their probability of survival to be? And add that up and divide by the number of people for whom I made the prediction. So my expected percent correctly predicted for survival is 67.3%. For fatalities, I do the same thing. I have to subtract 1 minus the probability here because remember, the predicted probability of the model is the probability of survival. And so in this case, I want to predict the probability that they died. So I've got 77% accurate prediction of fatalities. So I've broken it up for the EPCP of survivors and the EPCP of deaths separately, as I discussed earlier, because I really want to know that those things are different. And they are. As I would have expected, it's a lot harder to predict survivors than it is people who died. I'd probably do a pretty good job on the Titanic saying everybody died, especially everyone in third class. So understandably, I'm doing a bit better among the fatalities. Out of sample is the exact same process. The only difference being that I use my predictions and my data set on the for the out of sample cases as opposed to the in sample cases. I just redo this all again, and encouragingly, these are very close to the original numbers. My correctly expected PCP for survivors in the out of sample data set is again almost exactly the same, about 67%. For fatalities, it's a little less, 74%, but still very good. So, and interestingly, in this particular case, the EPCP numbers are actually pretty close to the PCP numbers that we used with the 50% threshold, suggesting that 50% threshold actually might not be all that bad of a threshold to pick. Okay, so the last classification-based statistic I'm going to talk about today is the ROC, or receiver I think it's actually receiver operating characteristic. I always forget whether it's operator or operating characteristic curves. An ROC curve is in many ways a continuation of the idea expressed in the percent correctly predicted statistic, with the difference being that instead of choosing one threshold for classification, we choose them all. Every value of t from the lowest 0 to the highest of 1. And each one of those choices gives us different predictions, which some of which will be right and some of which will be wrong. And then we actually plot those correct and incorrect predictions against each other to see how we did. So just right here, the idea behind the ROC is to calculate a PCP for all choices of t. Now, suppose, for example, I've got some y's, and I've got some predicted probabilities for y that come out of a model that I've created. Call that pi hats. And so some of these y's, this is a dichotomous y, so I'm using a binary dependent variable model. And some of these y's are 1s and some are 0s. Okay? And let's suppose that I arrange these in order from smallest probability to largest. So this is like a 0.1, this is like a 0.12, this is like a 0.18, this is like a 0.2, and so on. Okay, so I've got my table now. And I might sketch in some lines here, just so you know that these are separated. So there is my data set and my predictions. Or actually my dependent variable, not the entire data set, my predictions. And what the ROC does is it says, all right, we're going to classify some cases as zeros and some cases as ones. We'll start with the lowest probability right here, 0.01. So the first threshold probability is, 0.01. Classify all these as ones and all these as zeros. And then it records true value, or two, not true values, two values. The true positive rate and the false positive rate. The true positive rate is the number of y hat equal ones, or I'm sorry, let me take that back. The number of y equal ones for which y hat equals 1. And the false positive rate is the number of, let me think about this actually. No, I got this slightly wrong. So the true positive rate is the number of y hat equal 1 for which y equal 1. And the false positive rate is the number of y hat equal 1 for which y equal 0. So true positives are I say it's 1 and it actually is 1. False positives are I say it's 1 and it's actually 0. Since these are both rates, we have to divide by some normalizing quantity to make these rates. And in the case of true positive rates, we're looking at the proportion of true positives as a proportion of the number of total positives. So that's the number of cases for which y equals 1. For the false positive rate, we're looking at the number of false positives as a proportion of the number of total negatives. So a false positive rate of 1, for example, would imply that every single case for which y equals 0 is classified as y hat equals 1. That's all false positives. So there's the TPR and the FPR. For a threshold of 0.01, actually I'm going to need to move this out of the way a little bit. This down here just slightly. The TPR is going to be what? Well, we've classified everything as a positive. So all the positives are correctly classified. So we're just going to have 1. The false positives, on the other hand, are also, every single 0 is going to be classified as a 1. So we're also going to have the false positive rate as going to be 1. So in other words, if I say every case is a 1, I always get the positives right, but I also get all the negatives wrong. Then we move the threshold up. So the next threshold we might choose, we could choose lots of different thresholds, but none of them is going to matter until we reach that case, where suddenly we're classifying these as 1s and we're classifying that one as a 0. So now, with a threshold of somewhere between 0.1 and 0.12, so we'll say a threshold of 0.11. There's actually a continuum of them between 0.1 and 0.12, but nevertheless. And actually, I should say there's a continuum here of all the thresholds less than or equal to 0.1. Anyway, so for a threshold of 0.11, we would get a true positive rate of what? Well, all the positives are correctly predicted except this one. It's really a positive, and we're saying it's negative. So the number of y hats equals 1 for which y equals 1, well, all the y hats equal 1. all the y equals 1s for which the collection of y hat cases equals 1 for which y equals 1 is all of them. So in other words, there are going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. But there are actually going to be 11 cases of y equals 1 because we have this one right here. So it's going to be 10 11ths, something a little bit less than 1. The false positive rate, well, we've only got one case where we're classifying it as 0, and actually we're classifying it wrongly. So the number of y hat equal 1s for which y actually equals 0 is going to be basically all of the possibilities again. So we're going to have 1 again. So we've actually made our true positive rate worse, but kept our false positive rate the same. Now I'm going to skip over a couple of possibilities here and move up to somewhere in the middle. So here we've got thresholds, we can say of 0.7 or maybe 0.65. Anything between 0.5 and 0.8 would work here. What would our true positive rate, what would our true positive rate look like here? Well, we're classifying all these cases as 1s and all these cases as 0s. So how are we doing? Well, the number of y hat equal 1s for which y equals 1, let's see, 1, 2, 3, 4, 5, 6, 7, 8. So we get 8 correct predictions. How many total 1s do we have? Well, I've got 9, 10, I've got 11. So I'm still doing pretty well on true positives. Actually, most of the positives are still being correctly classified. Hopefully my false positive rate has fallen off a lot here. So let's see, I've got the number of y hat equals 1s for which y equals 0. 1, 2. Out of how many are there? 3, 4, 5, 6, which is just 1/3. So as you can see, as the threshold moves up, we actually start to do better in both dimensions. We do a little worse on true positive rates, but we get considerably better in false positive rates. The idea of the ROC is to calculate all of these different possibilities to give us a full sense of all the different trade-offs for classification that we might choose to make. We can choose all kinds of different thresholds depending on whether true positives or false positives are more important to us. But we're going to make some, we could make some choice, but the ROC curve just says, well, we could just make all of them and see what happens. And then what we do is say, okay, well, let's plot these TPR, FPR pairs against each other. Here's the true positive rate. Here's the false positive rate. What we expect to see, actually let me just put in a 45-degree line here. If the model is a good classifier, then we should be able to slide this line into position that puts all the 1s on one side and all the 0s on the other side. So if you can imagine what that would look like, 0, 0, 0, 0, 1, 1, 1, 1, something like that. If we put the threshold right here, we would get 100% true positives and 0% false positives. So we'd have a line or a point right here. Now we could continue to slide the line to the left, and we would just be getting more and more false positives for every true positive rate. Like so. And we could slide the line to the right, and we'd just be getting more and more true positives at the same false positive rate. Or, I'm sorry, fewer and fewer true positives at the same false positive rate. Like so. So that is a perfect ROC curve. Perfect classification. Now suppose that these 1s and 0s were just randomly arranged. So we had like a 1, 0, 0, 1, 0, 1, 0, 0, something like that. Then as we slide these things around, what we expect to see is to do no better in terms of classification than a coin flip. So I'll change this to blue. And coin flips will follow this 45-degree line with the idea that any number of false positives will be the same number as true positives, because the positives are just being determined by chance. In other words, I'm shooting randomly, and half the time or 20% of the time I hit the right targets, and 20% of the time I hit the wrong targets. It's just always the same kind of, I'm just hitting it totally at random. My classifier has no discriminating capability. So what happens there is, if you can imagine this blue line, here I get one wrong. I have one false positive. Then I have one true negative and one false positive. So, and then I've got a bunch of true positives, but I've also got a bunch of false positives over here. So I'm just sort of, as I slide this line up, I'm adding to my true positive and false positives at virtually the same rate as I slide these things over and over, and I get these numbers calculating into my rate. Something in between looks like this. So the greater the area between the 45-degree line and the ROC curve, the better my classifier is. And this is often abbreviated as AUC, or the area under the ROC curve. Generally speaking, it's going to be between 0 and, let's see, it must be, well, you could normalize it to 1. So, but if we had a 1, 1 square, this should go up to a half. Right, so it's half of the area of a 1, 1 square. The more area under the curve, the better your fit is. So 0 is horrible. 0.5 is good. I have also seen, I think it's also possible for packages to measure the total area, like so. In that case, if they're measuring the total area, this will vary between 0 and 1. And I think actually this is what the R package uses. If we're doing the area under the curve in total, then 0.5 is actually awful and 1 is great, and everything else is in between. So it depends on exactly how this is being calculated. But I believe the standard for R is to use the total area under the curve, so 1 is perfect. 0 is actually worse than random, worse than a coin flip, and a half is what you would get according to random expectation. So now let's take a look at what these ROC curves look like for our Titanic example that we performed earlier in R. Okay, so I'm going to go ahead and look at the ROC curve for my logit model of Titanic survival, and I'm going to do it in and out of sample. And I do this using the ROC R, or rocker package. Again, not nearly as exciting as it sounds, sort of like the party package in that respect. The ROC R package, first of all, wants you to generate predictions in a format that's amenable to the construction of a ROC curve. So you feed in your GLM or whatever other neural network, whatever predictions you have, as probabilities into the predictions matrix, or the predictions argument, I should say, for this predictions function. And you also tell it what the right answers are. So this is the labels, it just corresponds to the argument for what Y actually was in this data set. So Titanic train survived is just a list of who all survived in the training data set. And my predictions are just corresponding probabilities of survival for each one of the passengers in the training data set. Then the perf argument, so once I generate that pred argument, the perf argument says I want to plot the TPR, the true positive rate, against the false positive rate, as in a typical ROC curve, and I save that as perf, a perf object. And then I just plot that in red, and so there's my ROC curve. You can see I've got the true positive rate on the x-axis and the false positive rate on the y-axis. If I want the random prediction line in there. I can add a dotted line at 45 degrees. That gives me a sense of what a pretty bad model would look like. The area under the curve is just the area between this red line and the 0 line, or the red line and the dotted line, depending on how exactly you're measuring this. And I believe that for the ROC R package, you get area under the curves between 0 and 1. So here are the arguments, and then, right, so performance, yeah, here's the list of available for performance measures. AUC should be somewhere in here. Yeah, here you go, AUC. So if I look at the performance object that I've created, this perf object, there's the alpha values, y values, x values, blah, blah, blah. I can ask it, I believe, to give me the AUC measure as well by just asking it for, let's see, measure, performance measures used for the evaluation, right. So I say, I want, oops, the AUC, like so. And there it is. The area under the curve is 0.8714. So as I suspected, it's giving me a value between 0 and 1. The closer to 1 you get, the better. So the area under this curve is 0.8714. Pretty good. We can see visually that you get, if I'm limiting my false positives to about 5%, I can count on getting about 60% true positive rate. This is not terrible, but not awful. Now let's look at out-of-sample performance. So what I'm going to do is just the same thing over again. I'm in fact going to add to this existing plot using the add equals true command on the plot function for ROCR. The only difference is I'm generating the prediction and performance metrics out of the prediction data set, the test data set, as opposed to the training data set. And as we would guess, the performance on the on the test data set is not quite as good as it was on the training data set because the model didn't have the advantage of being able to look at these data first before it got to predict them. But the curves are pretty close, indicating that actually the classification doesn't really fall off that much. And the area under the curve, 0.8323, is pretty close to the area under the curve for the training data set. So again, not terrible, not bad. Okay, so now we've done all the possible assessments. Well, okay, we haven't done all the possible assessments, but we've done all the assessments I'm going to do from the classification perspective. Now let's change gears and suppose that instead of assessing the people, sort of assuming that you're going to survive or die with certainty, we're going to assign probabilities to the chance of survival or death. And then we're going to look at how well the model does at predicting each individual person's chance of survival or death. So let's move on to this probability-based fit statistics now. So we're going to begin talking about the probability approach to discrete choice model assessment, or discrete dependent variable model assessment, by talking about the simple process of binning your data according to the predictions that the model makes about that data. So imagine that I've got a y. Oops, I don't want to use gray here. I've got a dependent variable that's binary, and I've got a data set. Oops, and I'm going to plot that data set according to the fitted predicted probability that y equals 1. And so you can imagine if I put a rug of points in here indicating where these observations are, I get something that looks a little like this, where the limit is obviously that the probability of y equals 1 is 1, and the left-hand limit is that it's 0. Now, imagine what I want to do is I want to compare this, my fitted predicted probability, to the actual empirical probability in the data set. For an individual observation, of course, I don't know what that is. If I knew what that was, I wouldn't need to run a model. So for this particular observation, I have no clue what that probability necessarily is. But what I might be able to do is create bins. So I'm going to put a few more observations in here. Imagine I divide these observations into, say, let's say 5 discrete bins. 1, 2, 3, 4, and 5. Now you can see there's roughly the same number of observations in each bin, and generally speaking we would arrange this so that there were exactly the same number of observations in each bin. So there might be something like, 10 or 20 observations in each bin, but a total of, in this case, we've got 5 bins, so 50 in the entire data set. And then what we would do is we would calculate the average y, or the proportion that y equals 1 in each bin. So we would calculate what's the proportion that y equals 1 in bin 1? Well, it's just the number of observations where y equals 1 divided by the total number of observations in that bin, or 10, right? So we get some kind of probability, some number. Let's say it might be something like, 20%. And there's our observation, our estimated pi for that bin. So we're sort of taking an approach similar to the CART model, where we create discrete bins and then we estimate pi in each bin with a simple proportion or average. So we do this for every single one of our bins. I'm going to move these out of the way here. The maximum obviously is going to equal 1. So I'm going to call that there 1. And the last bin doesn't quite get a probability of 1, but gets somewhere close. So this is like something like, 0.2. This might be something like 0.4, 0.6, 0.8, 0.9, whoops, 0.95, something like that. Then what we do is say, okay, is the average pi hat the same as the average pi in this bin? So the average pi, or probability that y equals 1, is just going to be equal to, for each bin, actually, yeah, better to write it the way I originally wrote it. Right, and for each bin. The average pi here, pi hat, is just going to be the average pi hat in the bin. So, for example, in this first bin, we see an empirical probability of 0.2. We might see an average fitted probability of 0.3. Here we might see, 0.25. Here we might see 0.6. Here we might see 0.55. Here we might see 0.7. And what we're looking for is for the average predicted probability to be the same as the average empirical probability in the data set. A good fitting model will produce bins where the average predicted probability is equal to the average empirically observed probability in all of these bins. So you can do this visually, by literally constructing the histogram that we just constructed and looking for a sort of linear relationship with a slope of 1. But I think the more common thing to do is to construct a statistic that's related to this idea, the Hosmer-Lemeshow statistic. Actually, I'll just go ahead and write this out. Hosmer and Lemeshow demonstrated that this process actually could generate a statistic with a known distribution. So the HL statistic, which I'll abbreviate here as just H, is equal to the sum over G in 1 to cap G, where G is the number of bins, of the observed Y equals 1 observations in the bin minus the expected number of Y equals 1 observations in the bin squared divided by the number of observations in each bin times pi G times 1 minus pi G. So, what do each of these numbers or each of these symbols denote? Well, G is the number of bins. OG is the number of Y equals 1 cases in group G. EG is the number of expected, well, actually I can just say, abbreviate this way, expected number of Y equals 1 cases in G, and this will be determined by the fitted values pi and the number of cases in the bin NG, cap NG. NG is the number of cases in the bin. Pi G is, the average pi hat in group G, where pi hat is just the fitted probability that Y equals 1. So Hosmer and Lemeshow demonstrated that this statistic, this sum, follows the chi-squared distribution with degree of freedom equal to cap G minus 2. So what we can do is calculate this statistic and then see where it falls in the chi-squared distribution with the appropriate number of degrees of freedom. The null being appropriate fit, good fit of the model, or an appropriate specification. So the statistic is built on the idea that there's going to be a certain amount of variation in this sum attributable to sampling variance, even if the underlying predictor model that predicts pi hat is correct. The alternative hypothesis is misspecification. I'll actually say misspecified model. So the point of the test is to only reject the null of appropriate fit when the observable data are a substantial deviation from a good fit. This histogram looks substantially different than it would be under a good fit, even accounting for the sampling variation that we see in all finite data sets. So let's get a sense of what this Hosmer-Lemeshow test looks like in the example that we've been following up to this point. All right, so what I've done here is I've included a function which is written by Peter D.M. McDonald of McMaster University to compute the Hosmer-Lemeshow statistic. And I'm going to do this for both in and out of sample predictions from my model of the Titanic survival. Now the default for most Hosmer-Lemeshow tests and for this function is to include 10 breaks, so 10 bins that we're going to estimate. And in our training and prediction data sets, we've got about 650 observations in each one. So we're looking at about 65 observations in each bin, since those bins are going to be more or less evenly spaced. And it'll do all the calculations for us, including telling us the chi-square statistic and the associated p-value with that chi-square statistic. So doing a test in sample, what we find is that the chi-square p-value is 0.816. And remember that the null hypothesis here is that the model is a good fit. And rejecting the null, the chi-square is a one-tailed distribution. So we're looking for small p-values that are, in other words, the chi-square sum is much greater than we would expect. Much greater than we would expect given given a correctly fitting model. In this case, we have no evidence for misspecification. The probabilities, the difference between the probabilities that we observe and the probabilities that we predict are very small in sample. But if we repeat this process out of sample, what we see is actually that there's a little bit of a difference. In fact, there's a big difference in the sense that we come to a different conclusion. The p-value here is very small, indicating that when we do out-of-sample predictions, there's evidence that the predicted probabilities are not necessarily a good match to the empirical probabilities in the data set. So one or more of our bins might be mispredicting probabilities. Now, there are a bunch of different ways that we could assess what the problem seems to be here. For example, we could try constructing a histogram where we look at the actual number of successes and failures in each case and the predicted number of successes and failures in each case. But as it turns out, we're going to be able to do a very similar thing a lot more simply by going to a non-parametric binning paradigm, and that'll give us a good sense of what's actually wrong with this model. So let's talk a little bit about an extension to Hosmer-Lemeshow approach to non-parametric binning. So the idea behind non-parametric binning techniques is just to extend the Hosmer-Lemeshow idea to cases where we don't define discrete bins in advance, but rather allow each individual observation to have its own sort of weighted a local window that serves as a bin. So for example, imagine again I've got observations ordered according to their predicted probability that y equals 1 here. And for each one of these observations, I'm going to actually put two things on the x-axis, on the y-axis rather. I'm going to put the actual value of y, and then I'm also going to simultaneously put my estimate of the empirical probability pi on this graph. So let's just start with the y here. So for every value of pi hat, there are going to be some y1s and some y0s. Something like that. So there's your, whoops, there's your 1 and there's your 0. And now imagine just fitting a lowest regression model to this data. So I don't want to belabor what a lowest model is. That's discussed in other lectures in actually another class. So you can go back and watch that video. But just to refresh your memory, for every point on the x-axis here, on this pi hat axis, For example, let's consider this point. We calculate a locally weighted average for our y observations, where the weight can vary. It can be an Apashnikov kernel or a normal weight or a uniform weight with a defined window, something like that. But essentially it's some kind of weighted average, and that becomes our prediction for pi hat. So in this case it might look a little something like this. And actually in the Heatmap fit package that uses this technique that I'm going to show you in R in a second, we actually do first degree local linear fitting. The simple weighted averages are 0th degree local linear fits, but we find for various reasons that the first degree fit works a little better. And if I superimpose a 45 degree line on here, so here's 1, whoops, I'm going to put this in black. There's 1 right there. So you can see the 45 degree line tells you where pi hat equals pi. A perfectly fitting model would follow that dotted line perfectly, right? For every single case, our estimate of pi hat should be a very good predictor of the empirical proportion of cases pi. If we undershoot that line, that means that pi hat is bigger than pi, so pi hat is overestimating. If we're on the upper quadrant here, we're underestimating. So this little example shows us that we're actually overestimating the probability that y equals 1 for most of the data set. The model is telling us that the probability of success, or in survival in the Titanic case, is smaller than it should be. What this is equivalent to doing in some ways is for every single observation, instead of putting all these observations into a bin, for every observation we construct a bin that's a locally weighted average of all the observations inside of this window, where the weight is given, by the normal or something, and then that height of that bin we've sort of constructed on the fly becomes our point on this lowest curve, and then we can slide the bin to the left or to the right to move on to the next observation and the next observation and the next observation and so on. So it's as though instead of grouping the observations into bins, we just make one bin. I'm sorry, take that back. We make n many bins, one for each observation, where the bin is specially constructed for that observation to give a very good estimate of the empirical probability pi that y equals 1. Now, if we're going to do this according to the procedure that we specified in our paper, mine and Andrew Pierce's paper, where we talk about this procedure, what we would need to do next is try to tell the difference between gaps in fit that are due to misspecification and gaps in fit that are probably just due to sampling variation. So imagine I fit a model where F is like the logit or something. Even if I get this model exactly right, just because of sampling variation, I'm not going to get every probability prediction exactly right. So here's my fitted model. And what I do is I draw a whole bunch of bootstrap samples, not out of the data set, but out of the model. So I say, okay, suppose this model is right. Let's do 1,000 or 5,000 or just some large number of data sets out of this model and then plot this lowest line for every single one of them. And the bootstrap data sets will be the same size as the original data set. So smaller data sets will have more sampling variation in them. But they won't come from that data set. It's parametric bootstrapping. It's coming out of this parametric model. So imagine I construct this lowest line for each one of these parametric bootstrap data sets. I get a whole mess of lines. 1,000 of them or 5,000 of them, some very large number. Then what I do is I compare those bootstrap lines to the line I just created. And I'm going to actually thicken this a little bit so you can see it better. Like that. Now, there's the 45-degree line right there. Now, in some places, like say in here or in here, the gap between the 45-degree line and the green estimated line for our data set, there is a gap. But that gap is well inside of the bootstrap replicants that we got out of our model. And so these gaps are probably just due to sampling variation. Well, actually, I don't want to say they probably are. I can say they are safely attributable to. But these gaps over here, if we look at, say, black's not an optimal color. Let's look at these gaps here. These gaps between the 45-degree line and our data line lie well outside of what we got out of our bootstrap replicants. So these are probably not attributable to sampling variation, because those gaps are far larger than what we would expect if we were taking a sample out of the target model. So what our Heatmap fit package does is to generate this plot complete with bootstrap samples for assessment of whether a gap is attributable to sampling variation for a data set. So let's take a look at what this would look like on our Titanic data set. Okay, so here's the Heatmap fit function, and I'm going to let this go for a while because it takes time to do these bootstrap replicants. All I do is, you see, I just give it the formula that's associated with the model, and this assumes a GLM type model, so I'm going to use the family argument to tell it I want a logit model here. And I'm going to specify that I want this fitted on the training data. So one of the current disadvantages of this package, I haven't made the necessary changes yet, is that only is able to do in-sample assessment. In other words, I can't do out-of-sample predictions yet because there's no way, the program is not designed to fit a model on one data set and then do predictions on another data set. I could make that change, and someday I will, in which case I'll update the video. But for now, it only does in-sample data. So here's the plot that we generated. The darker the line, the further this line is to the edge of the bootstrap replication data set. And what you can see here is that the line is very nearly white over its entire length, which means that it's almost dead in the center of all the bootstrap replicants. Furthermore, there are no gaps. There are virtually zero gaps between what the logit model says the probability y equals 1 should be and the empirical probability we observe in the data set of the probability that y equals 1. So in sample, we're finding this is an excellent fit, just like the Hosmer-Lemeshow statistic told us. So it's good news. But now, if I try to do out-of-sample fit assessment, I can't do the bootstrap portion, but I can certainly construct a lowest model the same way that I described in the notes. So what I'm doing here is just dropping the missing data from the lowest model, and then predicting a lowest model out of the Fancova data set using the lowest function in Fancova on my predictions as the fit variable and y equals 1 or 0 as the y variable, using a first degree linear approximation for the lowest function. I save those predictions, I put them in order, and then I plot them. So in other words, I'm just sort of doing the thing that the Heatmap fit statistic function does, but I'm just doing it manually. And so this is the out-of-sample fit statistic, a Heatmap fit statistic. Then the problem you can notice is that I don't have the bootstrap replications, so I'm not sure whether these gaps are attributable to sampling variation or misspecification. However, I can get a sense of why that Hosmer-Lemeshow statistic was finding problems, was sort of reporting that the specification was bad out of sample. It's probably because, as you can see, over the entire length of, let's say, probabilities greater than about 0.2, this model is tending to overpredict survival. So for people that have, say, an 80% chance of survival, only about, let's see, 0.8, only about, let's say, 70 to 75% of them actually survive. For people that have, say, a 50% chance of survival, only about 40% of them actually survive. So we're overshooting survival probabilities over a fairly wide range of the data set. You can see these rug of points tells me where the data are located. On the other hand, the people that are on this end, very low probability of survival, I'm actually slightly under-predicting their chance of surviving. So if my model says, my logit model says you have a 5% chance of living, in actual fact you have closer to a 10, maybe even a 15% chance of living. So the model is missing out on some aspect of the process here, because it's tending to tell the predicted fatalities they have a greater chance of dying than they actually do, and it's telling the survivors that they have a greater chance of surviving than they actually do. So that gives us some sense of what that Hosmer-Lemeshow model, what that Hosmer-Lemeshow test statistic might have been picking up in the out-of-sample case. Even though the fit in sample is tremendous, there might be something missing from this model that's hampering its ability to really nail the out-of-sample predictions in a way that would be optimal. That's it for discrete variable model fit assessment. I hope you enjoyed this lecture, and I'll see you next time.